everybody, it's Mrs. Avon. We are going to start Chapter 6, Section 2, which is Circular Motion, by reviewing what we have already learned about speed and velocity in linear terms. Before we start talking specifically about speed and velocity, we should refresh our memory about the two types of quantities in physics. The first type is a scalar quantity. Those are just numbers, they don't have any direction. Some examples of those would be time, mass, speed, distance. Those are all scalar quantities that we've talked about. In addition to scalars, we've also studied pretty extensively vectors. And vectors have both magnitude, which is a size, just the numerical value, and direction, which is typically expressed as a positive or negative, but we know we can also use unit circle directions or north, east, south, west, or right or left to indicate the direction. And we should also remember that vectors are represented by arrows. We are going to focus in on two specific quantities, one scalar and one vector, to start out the section on circular motion. We're going to start with speed and velocity. Speed is a scalar term. It's how fast an object is moving. We should recall that speed is measured in meters per second, which means it is an indication of how much distance is covered per unit of time. So if I want an equation for speed, it's distance divided by time. Velocity, in addition to being how fast an object is moving, it also indicates the direction in which the object is moving, and therefore it is a vector quantity. So what we're going to look at first is how do we apply these variables to circular motion. We know that speed is distance divided by time. So if I'm moving in a circle, the question becomes, what distance do I cover, and how do I measure time around a circle? When we study circular motion, we are going to be looking at what is called uniform circular motion. That means that all the problems that we will look at have a constant speed, but a changing direction. What that means is when I calculate a numerical value for their speed, it's not going to change. But because they are changing direction, that means their velocity is changing. Say that again, that's very important. You should write that down. They have a constant speed, but they are changing direction. They're moving in a circle. So the direction is constantly changing. Therefore, the speed does not change, but the velocity does change because of the direction. So in order to find the magnitude of a speed of something moving in a circle, it's distance divided by time, but the distance that you cover is called the circumference of the circle, which you might remember from geometry is 2 times pi times the radius. Keep in mind that the radius is half of the diameter. Sometimes they may throw in a measurement of the diameter. And if you remember, we've talked about before that T, capital T, is the period, which refers to the time it takes to complete one revolution. So that's how we find the magnitude. We use the same equation, d over t, that we've been using since Chapter 2. The only difference is the distance is now the circumference, which is 2 pi r, and the time is the period, or how long it takes to complete one revolution. The direction we already should understand by our knowledge of Newton's first law. The direction of velocity is always the direction of motion of the object. So Newton's first law says that an object in motion will stay in motion in a straight line unless acted upon by a force. So if I'm moving in a circle, there has to be a force acting on me. Otherwise, I'd be moving in a straight line. So at any point on the circle, if you remove the force, let's say it's a string and you cut the string, you're going to move in a straight line that is tangent to the circle. We've seen this before in the sublevels. In the sublevels, what we find is they had a golf ball picture, talked about a golf ball rolling around a cup. Once it leaves the rim of the cup, according to Newton's first law, it's going to travel in a straight line. So when we look at the velocity vectors for an object moving in a circle, they will always be tangent to the circle, and they'll be pointing in the direction that the circle is moving. So this circle is moving clockwise. We could also see circles that would be moving counterclockwise, and the velocity vectors would just have the opposite directions. So make sure you pay attention to that. The last thing that we are going to look at for the speed of an object in circular motion is how those variables are related. Because 2 pi r is in the numerator, it is directly related to the speed. So if I take an object and I double the radius and I keep the period the same, that's going to increase my speed. Those are directly related. The period, however, is inversely related. So if I keep the radius constant and I change the period, it's going to inversely affect the speed. So if I increase the period, that will decrease the speed. If I decrease the period, that will increase the speed. So it's important when we're using these equations to understand their relationships. So this should help us with our introduction back into speed, velocity, and motion. Only this time we're going to have motion in a circle.
And Mr. Black's sneaking in a sample problem at the end. All right, so here it is. A rather reckless dude sits on a merry-go-round that is rotated way too quickly by a moving van, pulling on ropes spooled around the merry-go-round. Hey, I didn't make this up. This is actual video. The merry-go-round has a radius of 1.70 meters. At top speed, it has a period of 0.85 seconds. What speed describes the circular motion of this merry-go-round? Let's go ahead and pause it and see if you can solve it.